Okay, we're going to be talking about a few more things on vapor-liquid equilibrium. One is a little sort of scenario that I'd just like to talk about before moving on to other things. Right, this is a situation where we describe it as vapor-liquid equilibrium with one condensable component. In this case, it would be water and not the air. Now, one sort of thought experiment that I always like to do is that at 1 atmosphere and 20 degrees C, what phase of matter is water in? Pure water. This is liquid. So the question that I have is, for some of you in the class, you have this in front of you. Why does water evaporate? It wants to be a liquid. Why does it evaporate?
There's not a lot of water.
Yes, in a
the
sense,
air.
yes. But in terms of the mathematical framework that we're talking about, this analysis, does it assume a single component or a multi-component? Single component. Is this a single component system or a multi-component system? Things behave weirdly in multi-component systems. That's the short answer. So water normally by itself would never want to be in the vapor phase under these temperature and pressure conditions. However, when you mix it with air, then some of the water will move into the vapor phase because it's now a multi-component system. Now the assumption that we make here is that the air is only going to have a limited impact on how much it dissolves into the liquid. We call that the one condensable component. Now in the case of water evaporating, there's a big difference between this system that I drew here and the one that I drew below. What is that big difference? Right, so this one here has a finite quantity of air. This one has an infinite quantity of air. So if I were to leave a glass of water open in Utah, it's going to try and saturate all of the air, between the Wasatch Mountains and the Yoker Mountains. And it's not going to be able to do that. Right? So that's why water will evaporate very quickly in Salt Lake City, because it is a multi-component system. In the closed system, water is only going to evaporate such that the partial fugacity of water in the vapor phase is equal to the partial fugacity of water in the liquid phase, and then it's going to stop. But in the case of a glass of water open to the atmosphere, you'll never get to the point here where you're going to be fully saturating that airstream. It's always going to be limited to some extent. Now, the approximation that we'll write, if we use Raoult's law behavior, I'll put W as opposed to H2O. X water times the saturation pressure of water, mole fraction in the vapor phase multiplied by the system pressure. Now we'll repeat this example for, let's say, air. There's a couple of problems. Number one, we don't have a saturation pressure of air because it's supercritical. The concept of that doesn't exist. Two, because air does not want to be a liquid at all, it wants to be a supercritical fluid. This is also a very, very small number. So instead what we do in the one condensable component approximation is we say that the mole fraction of water is just approximately equal to 1. Meaning that at equilibrium, the saturation conditions is just equal to the vapor pressure over the system pressure as a function of temperature. So when we have a scenario here of one volatile species with a supercritical fluid, right? This could be an organic solvent in a tank, and you want to know how much of it is in the mole in the vapor phase. This is the approximation that we'll use. One condensable component. One. So for humidity, this is the starting point. based on how humid it is. So things like relative humidity, this is going to be the mole fraction that it currently is divided by the mole fraction of the fully saturated system. Absolute humidity would be doing a material balance on this, determining how much mass of water there is per cubic meter of air, for example. But this is the starting point for all of those calculations. All right, but the short story here is that multi-component systems behave strangely. Much more strangely when we start to look at liquid-liquid systems. All right, the one thing I wanted to go over today, before letting you all have plenty of time to decompress, so in general, at an undergraduate level, a flash calculation has a very specific meaning, which is a flash drum, where we have a feed. Typically this is a liquid. It flashes in a drum at a constant temperature and pressure to a vapor phase and a liquid phase. The feed, again, I like to use the composition of Z. It keeps the nomenclature consistent between our TXY and PXY diagrams. Liquid, mole fraction is X. Vapor, mole fraction is Y. We abbreviate this as V, L, and F. Generally, we set this equal to 1 to simplify our calculations, but it doesn't necessarily have to be so. Now, this is what we conventionally think of as a flash calculation, but in reality, a thermodynamic flash calculation is any system where you're calculating the composition and quantity of the two phases. So you can have a liquid-liquid flash, you can have a solid-liquid flash, right? A flash calculation is just basically a shorthand term saying for solving the phase equilibrium and figuring out how much of each of the two phases we have. This is the most common unit operation. One example would be when you're producing oil coming out of the ground, there's a lot of gas that's associated with it. What you'll do is you'll flash and you'll separate the liquids that are easily transportable from the vapors. Unfortunately, in some areas, those vapors just get burnt as a flare because it's too expensive to capture and to transport them. In some instances, you'll have a secondary gas pipeline to collect them as well. But that's one example where flash separator is really useful. So a flash separator in a liquid vapor form is really convenient when you have a fluid that is highly volatile with one that is not very volatile. Right? So if you're synthesizing, let's say, a polymer from, light species, the monomeric species, you could probably separate a heavy molecular weight polymer from lower molecular weight monomers. Another example there, right? For any sort of separation where you have two species that have similar volatility, and by similar I mean with vapor pressures within a factor of 2, 3, or 4, you'll probably want to go with a distillation column. But this is for separations where you have volatility differences like an order of magnitude different, like 10 times more volatile, which means you would only lose approximately 10% of your product here. That's a really, really back of the envelope way of thinking about it. All right, so all we are doing is solving exactly the same thing. Effectively, we're either solving a TXY diagram or a PXY diagram based on the feed composition, based on the liquid composition, based on the vapor composition. So what we talked about earlier in the week is exactly the same. Same equations, same everything. The only difference is we're going to be adding in the complexity of how much liquid and how much vapor we have. If we had a TXY diagram, we can solve a flash calculation almost instantly just looking at the TXY. Same thing with the PXY. Does that make sense to everyone? So what we're going to do then is just write out the equations, and they're going to be exactly the same. So we have mass consistency. All of the mole fractions have to add up to equal 1. That's just the definition based on how we define the mole fraction. We can have mass and mole balances. So we can have a total balance, the total mass or number of moles. In the case, if there's no reaction, we can substitute mass and moles pretty much interchangeably. If there's a reaction, we can't. same number of moles or mass coming in has to be equal to the same number of moles and mass coming out. This is just based on assuming a steady state approximation. And we can also write species balances. The number of moles entering, let me add an F here. The number of moles, oh, sorry, that is not right at all. Let's go with that. Okay, this is a different way to write it. The number of moles of species I entering the system in the feed is equal to the number of moles leaving in each of the two individual streams. The third way we can write this is we can say these two equations are 100% equivalent. The only thing is we're writing it in a slightly different way. We're saying the mole fraction by total number of moles, same approach there. But this will give you Ni of F, Nil, Niv. And lastly, we have our vapor-liquid equilibrium relationship, which is that the partial fugacity of species I in the liquid phase is equal to the partial fugacity of I in the vapor phase. So the entire course of your separations class as an undergraduate is built on this starting point and recognizing that there are mass transport limitations to reach this equilibrium. So in all the calculations that we're doing, we're effectively assuming that our separators are infinitely sized. But in any real world scenario, you have mass transport limitations such that the liquid and vapor don't have enough time of contact to obtain this goal. So what we're looking at is the theoretical maximum, which would be assuming that this is infinite in size, infinitely tall basically. And 100% well mixed on the inside, and we wait for a long time. Now, for most of the vapor-liquid equilibrium we'll be looking at, we'll have two different ways of approximating this for Raoult's law. And the other way we'll look at it is for non-ideal systems. Non-ideal vapor phase, non-ideal liquid phase, ideal liquid and vapor. This is our general relationship. So the key thing is, all we need to do is effectively a degrees of freedom analysis. Right, so we have three equations in our mass consistency relationship. For our mass and mole balance, we have an I number of equations. You have one independent equation per species in the system. That's not I, let's write C, the number of components. You get one equation per species in the system. This equation here is just adding up all the others, so it's what we call a dependent equation. It's not an independent relationship. And then for your vapor-liquid equilibrium, we have a C number of components. So what we need to do then is provide, let's see if I don't mess this up, so our degrees of freedom are going to be equal to, let's write it this way. I'll just basically, so what we need to do is we need to define enough variables here. I'd have to count up all the variables and unknowns. I don't want to do that right now. But basically, we have to define enough so our degrees of freedom are equal to 0. So 3 plus 2c, I guess, number of unknowns. But it can be more complicated, particularly if you start to look at non-ideal systems. All right, so what I will show very quickly, and let everyone go on their way, is for a two-component system, an A-B mixture, this is pretty trivial. I trust that every single one of you, given 15 minutes, sitting down, could hammer it out and figure out how to solve for whatever I asked for. The one that's tricky here is temperature, because it's nonlinear. It's a system of nonlinear equations. But if you're solving for anything else, pressure, composition, feed flow rates, vapor flow rates, liquid flow rates, it's just a system of linear equations. It's not bad. So with 2, it's pretty straightforward. When it goes to 3 or more, an arbitrary number, it gets a little bit tricky. So what we'll do is I'll show you very quickly here how we solve it for an arbitrary number of components as a general rule of thumb, and then you can use that for all future things. So for an arbitrary number of components, it is very useful to define something called the relative volatility. right? Oftentimes in a lot of trade manuals, this will be called the K factor. So this is like a common way to solve vapor-liquid equilibrium. This will sometimes be compiled into a chart, so you can just look it up. For Raoult's law, this will be equal to or for non-ideal systems, we can calculate it this way. So how we will apply this is we're going to use a series of equations. So we're going to say that F is equal to 1 to make it simple, in which case that we have the liquid flow rate is just equal to 1 minus the vapor flow rate. So if it doesn't leave as a liquid, it leaves as a vapor. That's all we're saying here. Simple substitution. We'll do one component mass balance. Okay. We will solve this for y. I'm not actually going to show the algebra because I trust that you can all do algebra. Solve for I. Okay, oh, sorry, let's see. I didn't finish this out here. Sorry. So when we substitute in the relative volatility, it'll get rid of the x in place of this k that we can calculate independently. And then we sub into summation of mole fractions of y is equal to 1. So basically here, this is where all the manipulation comes. But we can derive an expression here that will solve all of our vapor-liquid equilibrium flash problems. So in general, this is going to be able to solve our what I would call our standard flash calculation. So our standard flash calculation is going to be one where we know all of the feed composition and we're trying to figure out what the outlet products are. And this is going to be the most convenient way to accomplish that task. The relative volatility can be calculated just based on the system parameters. What is the temperature? What is the pressure? The feed is going to be provided. So the only thing that's going to be unknown in this circumstance is going to be the total amount of vapor. And then from here, if you substitute it along the way, you can solve for L, then you can substitute it into here, and you can kind of work your way down there from there. So this is going to be your general starting point for an arbitrary number of components. It is pretty tricky to figure this out without having it done a priori. But for two-component system, which is going to be the lion's share of what you'll be asked to do on an exam, you must be comfortable manipulating this on your own. But for a two-component system, right, you have your mass consistency relationships, you have two material balances. Here I've written it out in 3 different forms. You get 2 of these in any one of these number of forms you want to choose. And you get 2 vapor-liquid equilibrium relationships. In most cases, it's going to be 2 Raoult's law relationships. Then just solve for not only x's and y's, the composition of the 2 phases, but also the total amount of liquid and vapor. And then you have done your flash calculation. For a liquid-liquid system, the only difference would be that your vapor-liquid equilibrium relationship would no longer be vapor-liquid, it would be liquid-liquid, so we would approximate this using activity coefficients. But that would also classify as a flash calculation. Flash is a general term. It doesn't have to apply to only vapor-liquid systems. Let's see, and then the next thing to talk about would be distillation, but that takes a bit more time, so we'll talk about distillation a week from Monday. Any questions? Well, good luck on your exam and have a good fall break. See ya.